Okay, so let's take a look at the limit definition of the derivative and average rate of change. All right, so any rate of change deals with the slope, right? So I've got the slope formula there, y2 minus y1 over x2 minus x1. All right, we typically think of that as the change in y over the change in x, or rise over run. Right, so all of that is slope, and all of the slope is going to be a rate of change. All right, so this is really fundamental to calculus. To find the slope of a curve, wait a second, we can't find the slope of a curve, we can only find the slope of a line, right? So there's a couple things here that we have to think about. What we are used to is finding the slope of a line with 2 points, right? An x1, y1, and an x2, y2, right? So we typically have a line, and we typically have 2 points. Well, in calculus, that changes. Okay, we are now going to find slopes of curves. All right, and we are only going to need a single point on that curve to try and find the slope. All right, so obviously the slope formula that we have up above here, right, is not going to work because we need 2 points, right? But what if we use that slope formula and put 2 points really close together and made them turn into 1 point? So let me show you what's going on here. So here's this curve, right? So we have this curve, we'll call this curve f of x. All right, and we're looking for the slope of this curve at this green point. What is this green point? Could we call it x comma f of x? I think so, right? This is the point x comma y, or x comma f of x, right? So what if we were looking for the slope of this black curve at that green point? Can't do it. Why? Because we need 2 points, right? So let's put a second point really close to that first point, and then we will see if we can find the slope of the line that intersects both of those 2 points. How do you feel about that? So if we did that, what's the slope of this? I'm sorry, what's this second point called? Well, what if I called the x coordinate of this blue point x plus h? Would that be okay? And the h value is a very, very, very small value, right? An infinitesimally small value that is added to x. So if, let's just say if x was 3, x plus h would be 3.000000000000001. So h is a really small, super-duper-duper small value, right? All right, so if the x coordinate of this blue point here is x plus h, the y coordinate of that blue point would be f of x plus h. Agreed? All right, so again, if this is 3.000000000000001, then this up here would be f of 3.0000000000001. You get the idea. All right. All right, so if we have these 2 points and we're trying to find the slope of this red line, we could do that, right? So the slope of this red line, would be what? Well, it would be y2, which is f of x plus h, right, minus y1, which is f of x, right, over x2, which is x plus h, minus x1, which is x, right? So that would be the slope of that red line. But what if we wanted to take these 2 points and bring them super close together, because in the end, that's what we want to do, right? So I'm taking these points really, really close together. See how close together they are right now? Let me just get rid of this other blue. Oops. If I can see what happens here. I just want to get rid of that guy. All right, so let's go back to this here. All right, so let's put it kind of back where it was, right? These are 2 points. Oops, there we go. And now we're going to try to bring these 2 points really, really, really close together. What's happening to the h value? Well, the h is getting even smaller, right? And what happens as I let that value of h go to 0? Well, then they become 1 point, right? They become on top of each other. So as these 2 points, as this blue point moves closer and closer to the green point, the value of h becomes 0, right? And if the value of h becomes 0, what happens? Well, we've got one single point, right? And now if we're looking to find the slope of just a tangent line, right, just the slope of a line that intersects the curve in one spot, you know what, let me do this if you don't mind. Let me just change the color to purple, just because I had red there earlier. So now if this is the slope of a tangent line, what does a tangent line do? It hits the curve in just one spot. All right, what is the slope of that tangent line? Well, here's what they propose in calculus. The slope of that tangent line is still the same thing as we have up here. Okay, it's still that same formula, because we still do have 2 points, right? We have a blue point and we have a green point, but now they're on top of each other and h became 0, right? So here's what we're going to do here. So we're going to say that the slope of this tangent line, this purple tangent line, is going to be as follows. It's going to be the evaluation of the limit as h approaches 0 of f of x plus h minus f of x, right? Because again, remember, we have 2 points. You can't see the green point anymore because I moved the blue point on top of it. Why did I move the blue point on top of it? Because h is going to 0, right? So the difference between the 2 points is nothing. Over x2, which is x plus h, minus x1, which is x. All right, so this is an absolutely critical formula which gives us the slope of a tangent line on a curve. What does that give us? That gives us the slope of this curve at this single point, at this green/blue point, because h went to 0. All right, so let's just tweak this formula a tiny little bit and say that the slope of this tangent line, or the limit definition of the derivative, or the instantaneous rate of change, or the slope of a curve at a single point, is the following formula. Right? So all of this here is going to represent this formula. The limit as h approaches 0 of, just come back up here, right? F of x plus h minus f of x, right? All over, can we simplify that denominator? What's x minus x? Yeah, so when we simplify that denominator, that is what we get. All right, so this formula is now a new formula to find the slope of a curve at a single point. If we use that formula and if we evaluate this limit, as h approaches 0, we will find the slope of a curve at a single point, or we will find the instantaneous rate of change of a function. Right? Instantaneous means at a single point. This is called the limit definition of the derivative. This is also the same as the slope of the tangent line, because the tangent line intersects the curve at one point. All right, so you can see how important that formula is. It represents a lot of different things. Let's read what I have here. It says to find the slope of a curve at a single point, we need to bring the 2 points together to form a single point. I think I just did that, right? How can we do that? By evaluating this formula. So here's my limit definition of the derivative. No need to recopy this down, right? You already have it up above. It's the same exact thing as this right here. All right? So that's how we find the slope of a curve at a single point. That's how we find the instantaneous rate of change. All right, so let's do an example. Find the slope of the curve y equals x squared at the point 1, 1. So let's just think about what's happening here for a second, right? I think we all know what y equals x squared looks like. Okay. I think we all know where the point 1, 1 would be. Okay. So if we are looking for the slope at this point, it would be the same thing as looking for the slope of the tangent line. How are we going to do it? Well, we're going to use that formula, right? We're going to use that formula. The limit as h approaches 0 of f of x plus h, that's actually y2, right? That's where it comes from, minus f of x, that's y1. So this is really y2 minus y1. Over x2 minus x1, but remember when we did x plus h minus x, the x's dropped out when we just had h. Okay, so if we use this formula, we will get the answer to our question. We will get the slope of y equals x squared at the points 1, 1. All right, so let's do it. All right, so the limit as h approaches 0 of, what's f of x plus h? A lot of times people struggle with that. So to figure out what f of x plus h is, let's skip it for a moment and let's figure out what f of x is, because that's usually easier. What is f of x? What can I put down here to represent f of x? I'll give you a hint. F of x equals x squared, so instead of writing f of x, why don't I just write x squared? Pretty good idea, right? Yeah, that's what you need to do. Okay, so now let's go back to f of x plus h, right? So what's f of x plus h? Good question. Here's another question for you. If f of x is x squared, what's f of 11? It's 11 squared, right? What's f of 92? What's 92 squared? How am I getting this? Well, I'm just taking 92 and I'm plugging it in for x, right? What's f of a? A squared, right? Okay, so what's f of x plus h? Well, we're going to take this stuff, all right, and we're going to put it in for x. So if we take x plus h, and if we take x plus h and we substitute it in for x, instead of having x squared, we have x plus h, the quantity squared. All right, so this will give us the slope of y equals x squared, and then we're going to have to evaluate it at a particular point. So I'm just going to write that down. This gives us the slope of y equals x squared at any point, at any x value. We'll talk about the specific point 1, 1 in a second. All right, so first let's evaluate this limit. Can you do it? What's one way to evaluate limits? Well, you could plug 0 in for h, right? Plug 0 in for h, and what do you get? You get x squared minus x squared over 0. You get 0 over 0. That is not going to work, right? So plugging in 0 for h is a good idea, but in this particular example, it's not going to work. All right, so what are our other options? Well, we could start to tweak this a little bit, right? We could multiply out x plus h times x plus h, and if we FOIL that, we get x squared plus xh plus xh. That'll be 2xh plus h squared, all right? And then I'm just going to bring back in the minus and the x squared, all right, all over h. How do you feel about that? Is that okay? You want to plug in 0 for h? Yeah, that would be a bad idea, because if you plug 0 in for h, you would still get 0 over 0. So, not going to work. But let's keep doing some more algebra and see what happens. All right, so x squared and x squared cancel out, right? So we have 2xh plus x squared all over h. You have any thoughts for me now? Well, what if I factor it out in h? So the limit as h approaches 0 of pull out an h. You have 2x plus h over h. I can cancel these h's. And now we're looking at evaluating the limits as h approaches 0 of 2x plus h. Now what if we plugged in 0 for h? Well, now I think we would have it, right? 2x plus 0 or 2x. All right. What is 2x? What does 2x represent? 2x represents the slope of y equals x squared at any point. What point do we want to know about the slope of y equals x squared? We want to know about it at the points 1, 1. Right? So we're going to go back to 2x, which represents the slope of y equals x squared at any point, and we are going to evaluate this at x equals 1. And by that I mean we are going to take 1 and plug it into the equation for x, all right? So we get 2. So the answer to the question is 2. The slope of y equals x squared at x equals 1 is 2. The slope of this tangent line here is 2. The slope of this curve at this point is 2. All right. If we wanted, let's just say this said, hey, find the slope at the point, I don't know, 3, 9. What would that be? Well, x equals 3, right? So we're going to come down here and take 2x. All right. What does 2x represent? The slope of y equals x squared at any point. And we would evaluate it at the point 3, 9, or where x equals 3. And we would get a slope of 6. All right. What if we wanted the slope of the point at -2, 4? Let's see, it's probably right about here, right? -2 up 4. What's the slope of that line? Well, it certainly should be negative, right? Let's see what happens. We're looking for the slope at x equals -2. So we would come back to 2x, which gives us the slope of y equals x squared at any point, and we would evaluate this slope at x equals -2. So we would have a slope of -4 at the points -2, 4. What about at 0, 0? Think about that for a second. You don't even need calculus for that, right? What's the slope at 0, 0? Well, clearly it is 0, right? But I'll show you how this fits into this formula as well. We're looking for the slope at x equals 0. So we come down to 2x, which represents the slope of y equals x squared at any point. If we plug in 0 for x, we get 0. All right, so that's critical. That's the limit definition of the derivative. That is how you find the slope of a function at a single point, right? I have to use this formula here. All right, let's do a second example. It says here, in example 1, we found the instantaneous rate of change of the curve at the point, for the curve y equals x squared at the point 1, 1. All right, so just to recap again, we had y equals x squared. We were looking at the point 1, 1. All right, the slope at that point, all right, was 2 because the slope was 2x. We evaluated it at x equals 1. We got 2 times 1 or 2. Okay, so that represents the instantaneous rate of change. That represents the slope of the tangent line. That represents the slope of this curve at that specific point. A lot of different ways to say the same thing, right? All right, so in this second example, we're going to talk about the average rate of change as well. Now, I haven't defined the average rate of change for you, so let me do it right now. The average rate of change is simply y2 minus y1 over x2 minus x1, right? This is simply the slope of endpoints. All right, so when they ask for the average rate of change, they're just talking about what any algebra student would be able to do, right? To find the slope of 2 points. All right, so this example is going to ask us for the average rate of change. All right, but it's also going to ask us for the instantaneous rate of change. Okay, this is calculus. This red stuff is going to be calculus. Okay, this is going to be the limit definition of the derivative. Right? In blue here, it's just a regular normal algebra problem. All right, so let's do the red stuff first. What's the instantaneous rate of change of f of x equals x squared minus 3x at the point 1.5, at x equals 1.5? All right, so let's see here. That is going to be found by finding the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, this is a formula that you need to memorize. All right. All right, what are we finding? We're finding the slope of this curve at x equals 1.5. Do you want to see what that curve looks like? You don't have to, but if you wanted to see what this curve looks like, right, f of x equals x squared minus 3x, it may help you just to take a look at the graph of it. So if I set the equation equal to 0, solve for x, I'm going to find the roots. All right, so you know that it crosses the x-axis at x equals 0 and that x equals 3. Right? So it's a parabola. It's going to look something like that. Right? All right, so we want the instantaneous rate of change at x equals 1.5. Looks like it's going to be 0, isn't it? It looks that way to me. All right. Well, we'll see. So we'll do it using calculus. All right, so we're using this limit definition. All right, what's f of x? So as I go back to this formula here, the limit as h approaches 0 of, again, a lot of times people have trouble with f of x plus h. So a lot of times I personally just focus in on f of x first. What is f of x? F of x is x squared minus 3x, right? All right, so what's f of x plus h? Well, f of x plus h is going to be taking x plus h and plugging it into this equation for x, right? So if this equation is x squared minus 3x, what's f of 92? Well, it would be 92 squared minus 3 times 92, right? What's f of a? Well, it would be a squared minus 3 times a. What's f of x plus h? Well, it's x plus h, the quantity squared, minus 3 times x plus h, right? I'm just taking x plus h and I'm substituting it into the equation for x. All right, so x plus h, quantity squared, minus 3 times x plus h. All right, let me just erase this stuff if you don't mind. All right, so hopefully f of x plus h isn't all that bad, right? If you think to yourself, what's f of a? What's f of 92? And what's f of x plus h? It's the same concept, right? All over h, right? So I think we've effectively substituted in here, right? What do you think? F of x plus h is down here in purple. F of x is down here in black. You notice anything that maybe might be a little bit wrong? I need parentheses around f of x. Why? Well, because I'm subtracting all of f of x. So if I don't have parentheses around that, I would just be subtracting x squared. I can't do that. I need to subtract all of f of x, okay? So these parentheses are absolutely vital. You have to have them so that you're subtracting all of f of x. All right, so let's keep going. What do you want to do? You want to plug 0 in for h? Go ahead, you could plug 0 in for h, but trust me when I tell you, you're going to get 0 over 0. So we're going to have to do some algebra. Calculus is tough because there's so much algebra involved. What's x plus h, the quantity squared? Well, it's x plus h times x plus h, or x squared, plus xh plus xh, which is 2xh, plus h squared, all right? And then I'm going to do minus 3 times x plus h, which is going to give me a negative 3x and a negative 3h. Okay, then I'm going to distribute this negative, right, which is why I needed those parentheses in the first place, to give me a negative x squared plus 3x all over h. It looks complicated, doesn't it? Calculus is complicated, but it's really not complicated at all, right? We just FOILed this, you could do that. We just distributed a negative 3, you could do that. We just distributed a negative, you could do that, right? All right, once you do that, you're going to notice something that's going to happen. Everything that doesn't have an h, like x squared, is going to cancel. Everything that doesn't have an h, like negative 3x, is going to cancel. And what remains is everything that has an h. All right, so I've got 2xh. I've got plus h squared. I've got minus 3h all over h. It's simplifying now, isn't it? Maybe I could factor out an h from the top there. So if I factor out an h, I have 2x plus h minus 3. And now since I factored out that h, I can cancel it. And now I no longer am going to have the problem of getting 0 over 0. So now I can evaluate this limit. All right, now I can plug in 0 for h like I wanted to do at the very beginning. All right, so if I put 0 in for h, I get 2x plus 0 minus 3, or 2x minus 3. What does 2x minus 3 give us? It gives us the slope of f of x equals x squared minus 3x at any point. I'll write that down. This gives us the slope of f of x equals x squared minus 3x at any x value. What is the x value that we want? Do you remember? At x equals 1.5, right? Isn't that what we said? Here it is. We want the instantaneous rate of change at x equals 1.5. You know what 1.5 is the same thing as 3/2. I personally like to go with fractions instead of decimals. Just a little bit easier for me, but you can put in a decimal, doesn't matter. All right, so we're taking this slope of this function. I usually call it the slope of the tangent line, right? You can call it instantaneous rate of change. You can call it the slope of f of x equals x squared minus 3x at any specific point. Bottom line is it's 2x plus 3, and we're looking to evaluate this at x equals 1.5. All right, so at x equals 3/2. All right, so let's see here. We get 2 times 3/2 minus 3. See why I like to go with fractions, because that 2 and that 2 cancel. And we're left with 3 minus 3 or 0, right? We knew that that answer was going to come out to be 0 after we graphed the function f of x equals x squared minus 3x, right? Remember? So I guess we could take away that question mark now. And that actually is the slope, right? The slope is 0. And you may say, oh, if we knew that from the beginning, why would we need to okay, well, what if they asked you for the slope at x equals 1? What's the slope at x equals 1? What's the slope at x equals 0? What's the slope at x equals 3? All right, they're going to be different values, right? What's the slope at x equals 1? Well, remember, all right, our slope is 2x minus 3. All right, so if we take that and evaluate it at x equals 1, we're going to get 2 minus 3 or a negative 1. All right, so the slope at x equals 1 is going to be a negative 1. We could find the slope at x equals 3 if we wanted to, right? We could get crazy here. All right, what if we found the slope at x equals 3? Well, let's see, it would be 2 times 3, all right, minus 3, or 6 minus 3, or 3. All right, so that's the slope at x equals 3. So we could go anywhere. That's the beauty of this formula, is once we get, I call this the general derivative, or the general slope, or the slope of the curve at any x value. Once we have that, now we can go and find the slope at any x value. Right, the other thing that we need to do is to find the average rate of change, right? So we got a little crazy with the instantaneous rate of change. We need the average rate of change now from x equals 1 to x equals 3, okay? This notation tells us to start at x equals 1 and to end at x equals 3. All right, so here's x equals 1. Here's x equals 3. To find the average rate of change, right, we are just going to find the slope of those 2 points. All right, so in order to find the slope of those 2 points, I need the y coordinates. All right, so here x equals 1. What's the y coordinate? Well, I'm going to have to come back up here and figure out what the y coordinate is when x equals 1. All right, so 1 minus 3 is a negative 2, right? So there's 1 point. All right, and how about the other point? Well, looks like it's 3 comma 0, right? But just to be sure, plug 3 in. All right, what's 3 squared? 9. What's 3 times 3? 9. What's 9 minus 9? 0. All right, so we're just going to find the slope of these 2 points to give me the average rate of change. All right, and again, that formula is going to be y2 minus y1 over x2 minus x1. Okay, so that's going to be 0 minus a negative 2 over 3 minus 1. All right, so it looks like it's going to be 2 over 2 or 1. So the average rate of change from x equals 1 to x equals 3, or we also call sometimes the average rate of change the slope of the secant line, right? Because the secant line is a line that intersects the curve in 2 spots. So the slope of the secant line, or the average rate of change from x equals 1 to x equals 3 is 1. All right, so there you have it. You've got the limit definition of the derivative, which is the instantaneous rate of change, and then you also have the average rate of change. Again, the instantaneous rate of change is found by using the limit definition of the derivative.